Welcome to the supposedly last presentation on the third day of this beautiful event to wherever in the world you may be. I'm Patrick Lauer from the University of Wuppertal, Germany, and I'm going to talk about the role of the cost function for material parameter estimation. The members of the team that worked on this contribution are Tristan Hehn, Corinna Trittin, Fabian Brennström and Lucas Arnold from the University of Wuppertal and the Research Center in Jülich. What am I going to talk about in the next 15 minutes? The topic is the inverse modeling of bench scale experiments to estimate material parameters for pyrolysis simulation, for example, to compute flame spread. How this process works in detail, I'll explain in a minute. I'll focus on the cost function that determines the deviation between the experimental results and simulation results. Several different cost functions are evaluated for estimating material parameter sets that allows the simulation of pyrolyzation of solid polymers. So, what was inverse modeling again? The common approach is direct modeling, where parameters from experiments or literature are used to model something and get model response, the simulation data. But when we can't have proper parameters because we can't determine them directly through experiments, we have to calibrate a model to experimental data. Then we can use the obtained model parameters to generate a model response that fit to the experimental data. This is called inverse modeling. That is, in fact, the situation we have to deal with when we want to model pyrolysis. Please note, the obtained parameters are so-called effective model parameters and do not necessarily represent any real physical or chemical parameters of the virgin unburned material, and certainly not any of the intermediate materials that may be formed during the sample decomposition. So let's see how this process works in detail. This figure shows the workflow and the required interfaces to the optimizer, the target, experimental data, and the simulation model, including executable, the computing resource, and input file templates. One evaluation step looks like this. The optimizer is called to define a set of current parameter values to be evaluated. Models are executed, the simulation data is extracted, and then passed to the optimizer. The optimizer compares the experimental and simulation data and generates a fitness value. This is the cost function. The optimizer decides if further evaluation steps are needed based on the fitness value. So, we are not here for the first time. 6 years ago, we delivered a talk about the target data obtained from experiments and how to model this experiment properly in the fire dynamics simulator. That was Corinna Trittin, who talked about the influence of input parameters on the fire simulation at the FEMTC 2014. You'll find her presentation and paper with this QR code. Since we have to perform thousands of simulations, also in 2014, we covered the computational architecture on high-performance computing systems, where Lucas Arnold gave a presentation on performance analysis and shared memory parallelization of FDS. If you follow this QR code, you will find his presentation. 2 years later, we went into detail on the used optimization algorithms that generate the input parameters in a smart way so you don't have to test the whole parameter space randomly. It was me at the FEMTC 2016 in Spain that talked about the performance of optimization algorithms for deriving material data from bench scale tests. Today, in 2020, we want to give you some insights into the cost function, the main part that compares the experimental results and the model response. What materials and methods did we use? For the inverse modeling process, for our example, we choose to set 2 sets of experiments of black PMMA as targets for the inverse modeling process. The reaction kinetic parameters are based on TGA data in a nitrogen atmosphere. 3 heating rates were chosen to generate a robust parameter set across a large temperature range. Data obtained with the controlled atmosphere pyrolysis apparatus 2, kappa 2, under an external heat flux of 25 kilowatt per square meter was used as a target to generate the thermophysical parameters like density, conductivity, etc. Data of both experiments were taken from the condensed phase material database of the measurement and computation of fire phenomena group. Reaction kinetics for this were obtained from TGA data targeting 3 different heating rates in an inverse modeling process. It was simulated with FDS and modeled with 2 independent reactions. Mass and mass loss rate for the best fitting parameters can be seen in the plot on the right side. And we won't cover this process in detail in this presentation. With the reaction kinetic parameters from the slide before, we obtained the thermophysical parameters like density, emissivity, conductivity, specific heat capacity from a kappa 2 experiment with inverse modeling. As target, we used the 25 kilowatt per square meter experiment. For validation, a 60 kilowatt per square meter experiment. We calculated 3 cases with a different cost function each and did 25 repetitions for each case. And as optimization framework, we used Propti that was developed by us, and for the actual modeling, we used Fire Dynamics Simulator. And now I talked a lot about evaluation methods. Let's see some cost functions. This figure shows an exemplary mass loss rate of an irradiated sample as a function of time with experimental values y and model values y hat. For the most simple case, one single point can be defined as objective. The error is then the distance between the experimental value y and the model value y hat normalized to y. For example, this could be used for temperature at ignition time. The threshold method is quite similar to the single point approach. The first time y hat of t exceeds or goes below y of t0, the threshold value is used to calculate the normalized distance on x-axis between these 2 values. If the condition is never met, the assumption is that always the largest difference is applied. Such a cost function could be used for time of ignition, for example. The root mean square error, RMSE, is a measure for the difference between values of 2 data sets. It adds up the squared distance of experimental and model data points, divides it by the number of data points, and normalizes the square root of this to make it scale independent. But a strict comparison of experimental and simulation data will never reach 0 values. What would be a perfect fitting? To face this aspect, a cost function that uses a data band is introduced. Assuming uncertainties in the experimental and simulation data, this is not limiting the quality of the inverse modeling. Yet, a less stiff system could lead to benefits like quicker convergence and robust solutions. Bands, what we called it, rates any value between a lower and the upper boundary, as can be seen in the figure, as perfect fit for a given point. Otherwise, it uses the actual distance. Whereas in the other concept, we call it range, that rates y hat with a deviation of a factor r to y, the experimental value, as perfect fit. Otherwise, it uses the actual distance. And since all these cost functions are normalized, we can use more than one on one or several data sets and simply add them up. As seen in this figure, we use all the methods presented before. RMSE bands on the first part, then RMSE range in the middle part, at the end a standard RMSE, and then a threshold value and a single point comparison. So let's come to our evaluation. What cost functions did we evaluate? We did inverse modeling with RMSE, then with a range of 5% around the experimental data, and the band consisting of upper and lower boundaries given by the uncertainty provided with the experimental data. In this plot, we show the best resulting massless rates against time of each evaluation. Experimental values are blue, results of bands is green, results of range is olive, and the results of RMSE is red. As you can see, there is next to none difference in the best fit. The results of the validation simulated at 60 kilowatt per square meter are shown in this figure. In general, the responses are very similar to each other as in the 25 kilowatt case. However, all cases show significant fluctuations before the material is used up. And what you can see here is a lot of data in the table. It shows the best and mean thermophysical parameters and the standard deviation for the 25 repetitions of the 3 cases. First row shows the overall fit, then the upper 7 rows the parameters for the unburned material. What I want to show you here is that for the unburned material, all parameters are pretty similar and all standard deviations are really low. So we get a pretty high robustness in all of the cases. And looking at the cumulative minimum of the fitness value over the 25 repetitions for each of the cases, none of the discussed cost functions stands out in terms of how fast they converge to their respective minimum. All need about 10 to 11 generations to converge. So let's discuss our simulations. Different cost functions are investigated with respect to their performance in finding material parameter sets. For the chosen example case here, none of the different cost functions significantly outperforms any of the others. The best parameter sets within each cost function group, as well as across these groups, show nearly the same simulation response. Looking at the cumulative minimum of the fitness values, none of the discussed cost functions stands out in terms of how fast they converge to their respective minimum. Thus, no useful statement as to how fast convergence is reached can be made here. But for a larger number of optimization parameters, this behavior might change. Larger sampling limits for the individual parameters might have stronger effect on the convergence when choosing different cost functions. And the experiments were conducted in an inert atmosphere, and in the simulations, the gas phase reactions were neglected. This could contribute to an oversimplified modeling of the involved processes, leading to a more trivial case. So let's see it in a more generic way. A cost function that uses an area as a target provides means to incorporate the uncertainty observed in the experiments. RMSE requires exact matches of the data points, while slight variations in the other cases could still fall inside the target area. Bands and range could be useful to account for variance that is encountered when repeating a single experiment multiple times and allow for its representation during the inverse modeling process. The ability to combine cost functions in different ways allows to target multiple values, like heat release rate or surface temperature, as these may be of crucial importance for the real scale applications, especially for flame spread modeling. So, what can we recap? 2 newly implemented cost functions were evaluated against the commonly used cost function. They compare the modeled data against an area, not a data series. But no significant difference in performance, robustness, and results was observed for the investigated cases. Still, this is useful to take experimental uncertainty into account. It might also provide an advantage in performance, robustness, and results in more complex cases. All the data we produced with this contribution you will find in the Fire Safety Engineering and Evacuation group on a website called Zenodo. And you might get quick there with this QR code for the framework for inverse modeling, or this QR code for the dataset repository we provide as well on Zenodo. So, thank you very much for your attention.
Any questions for those joining us from the stage? Feel free to put those in chat and we will have those answered as best as possible. I had a question as I was watching this before, if maybe beat other people to it, about how long does it take to run through the convergence calculations to find, just once you put the data in, how long until you say, I have some good data for that I'm confident matches well?
We are running it on a 24 core machine, and it is like up to 4, maybe 6 hours.
Okay.
Yeah.
Okay, great. And then what experiments do you typically use as input?
What do you mean by
I think he means like what experimental data sets or like what methodologies do you typically use to then get the data that you use as the input for matching?
Yeah, usually what was presented, TGA, cone, and as we took the data, because we hadn't had the chance to do our own experiments, or we wanted to stay connected to the MagFP working group, we used the kappa-2 and TGA experiments from what was provided from the MagFP group.
Okay, great. So a collection of resources to a collection of data types, data sets. Excellent. Yeah, I think that's kind of the hard part, right? So Kevin's asking here, can you use the cone alone? Like if you just had cone data, would you be able to?
Cone alone just for reaction kinetics as well. We did this in the past, but it didn't converge to any credible values that could be scaled up for something. So yeah, we're still working on that, just using cone data alone, but we didn't found that there was a better fit using cone alone compared to using first reaction kinetics from TGA experiments and then putting just the cone for thermophysics, physical parameters. Yeah, so we did use it, but it is not the best results we got from it. Yeah.
There's another question here about, is there a plan to integrate this method into any mainstream tools that can be used by others in the field?
Since it's pretty well documented, we use this inverse modeling framework property we developed for some time now. You could use it for anything that you want, and it's open source, free to use, and kind of well documented. So feel free to go on GitHub and check it out.
It's only not mainstream because everybody's not using it yet.
Yeah.
As soon as everybody uses it, then it'll be mainstream. So yeah, but it is available. That's good to know. And I suppose there could be integrations with something else where you could, yeah, and I thank you for posting the link there, where you could, provide it data files, make a nice UI for it in some other tooling, like for example, maybe Pyrosim. When you're building your material library, you could have some way of kicking that off and then creating like some other integrations. But for now, it's just a nice tool you can use independently of others to develop your data.
Yeah.
That's great.
But yeah, you're free to integrate it in whatever you want.
Whatever, sure. Sure. And it may actually be kind of a nice web service too, as I'm thinking about it, a way of like sending, data files, uploading, and then having those just generate on some cloud computing resource and then coming back with estimates.
Connected to a cloud and then, yeah.
Yeah.
I mean,
like an instance that you call or an API you send data to and it spits back results. That might be interesting.
Yeah. But first, then we should figure out the best method to get the material parameters for pyrolysis simulation. And I think we are not still there. And yeah, there's nothing to sell with that, I would say.
Right. Well, and yeah, that's always been a hard part is like, okay, I mean, even Kevin's question kind of leads off to it. Like, well, what experiments do I run? What do I do with that data? How do I, that entire methodology, not just the estimation, but the whole entire method from beginning to end has to be defined well, I think, still. So.
And then being able to scale it up. Yeah.
Yeah, that's interesting. All right, any other questions? Anybody else? About 36 people here. Okay. I'll give it. There always seems to be, as soon as I say, okay, let's wrap it, then there's always another question hit. So I'm going to see if I can trick it. Okay, let's wrap it up. Yes, I got it. Oh, no, it's a good question. Oktoberfest at home beer recommendations. Okay, that's a perfect question. Yeah, that's a perfect question to end on. Any recommendations for beer?
If you can get it there where you are, get some beer from Hoppebräu. It's at Tegernsee, but it's not Tegernseer beer. So, yeah.
That's the recommendation. That's perfect. All right. Well, with that, thank you very much. Thank you for the talk. Thanks for the continuing information that you do throughout the years here, giving us more information as you go. And thanks for your time here with the Q&A. Really appreciate it.
Yeah.
So we'll see you later. Thanks.
You and the whole team for organizing and having us again and again. Yeah.
Thank you. I appreciate it. All right. See you soon, Patrick. Thank you.
See you soon.
Bye-bye.
Bye.